For some stars, that's as bright as they will ever get. If they do not have enough mass, less than 1/10 the mass of the Sun, they can never generate nuclear fusion in their cores, which means there is no internal source of heat. The star is doomed to simply cool off for the rest of its life. Astronomers call these stars brown dwarfs, and since they cannot sustain nuclear reactions, some astronomers argue they are not really stars at all.
The fact that stars look redder as you begin to look through dust is called interstellar reddening. And it's a very important effect that allows us to tell how much dust is between us and a star. Reddening is just what it sounds like. It makes the light from the star redder. So if you were just looking at the star would look redder, a little bit like the way our sun looks redder at sunset.
Besides reddening the light from stars, the dust also dims it. If there is enough dust between a star and the Earth, the starlight can be totally blocked. Astronomers call this process interstellar extinction. Nebulae are classified into three main types based on how light interacts with the dust and gas of the cloud. The easiest class of nebula to understand is the dark nebula. These are dense clouds of dust and gases that block the light from stars that lie beyond them. These nebula also provide excellent examples of interstellar reddening, as seen in this image. Because there is no interaction with visible light beyond interstellar reddening, little data can be gathered from direct optical observations of dark nebulae at visible wavelengths. Infrared and radio observations are used instead to determine what lies beyond the nebula and provide information about its structure. The other two classifications of nebulae involve the interaction between starlight with the gas and dust that makes up the nebula.
The distinction between an emission nebula and a reflection nebula is not so much the gas itself or its distribution in space, but it's the spectrum of the star that is embedded in that gas. If that star is of fairly low temperature, then the energy field of that star is not sufficient to ionize the hydrogen gas in surrounding the star, in which case the light is basically being reflected largely by interstellar dust particles and reaches the observer with basically the original spectrum of the star that is illuminating that reflection nebula.
A reflection nebula simply acts as a sort of mirror, reflecting light from a nearby star or stars, and tends to be blue due to the fact that blue photons scatter more easily. This characteristic blue light is an easy way to distinguish a reflection nebula from a hotter emission nebula.
If the star, however, is hotter and therefore its spectrum contains a larger component of ultraviolet radiation, that ultraviolet light can ionize the surrounding hydrogen. And in that case, a whole new series of spectral lines, emission lines of atomic hydrogen appears in the spectrum, and we get the characteristic red glow.
Emission nebulae are often referred to as H2 regions because the hydrogen in them is ionized. Protostars often form in clusters in dense clouds, measuring up to a light year in diameter, containing 10 to 1,000 solar masses of interstellar material.
These dark clouds are the so-called Bok globules, very small, isolated and very dense small molecular clouds that really look like almost black dots. These are very dense cores of molecular clouds, often in situations where the rest of the molecular cloud has somehow been destroyed or stripped away by external forces.
These dense clouds are the cocoons, shrouding the activity of the formation of the stars encased within.